Good day, students. Welcome to General Science 101. What we did last time was we looked at different aspects of optical aspects, in fact, of refraction of light. We looked at the process of refraction. We said when light enters from a lighter medium to a denser medium, it changed direction. This changing of direction is basically what is refraction. We looked at the laws of refraction. We looked at Snell's law. We looked at different ways of finding the refractive index. Refractive index, of course, is the ratio of the sine of the incident angle divided by the sine of the refracted angle. It is also the speed of light in air divided by the speed of light in a medium. These are ways and means and techniques of finding the refractive index of material. We also discussed what is a critical angle. Critical angle basically is the angle when coming from a denser medium to a lighter medium, the light bends so much that it does not leave the medium. In other words, whenever a light is restricted within the medium, the denser medium, of course, then we say that the angle at which it is striking the medium is greater than the critical angle. The critical angle being that angle where the light just goes parallel to the boundary. The uses of this refraction of light, of course, we went into lenses and we looked at mirrors and lenses, and henceforth we formed the lens equation. And the lens equation basically we found out was identical to the equation which we formed for the mirrors. This lecture is going to be the final of this series. We are going to be looking at application of lenses. We are going to look how we use lenses, where we use them, and the most common use which we have is for these spectacles, how we look at different effects in the eyes, and how do we correct them using lenses. Now, just a little bit of recap. We said then when light enters from a lighter medium to a denser medium, it bends, it changes direction. And we use this aspect to form lenses. If it is bending towards the normal, we say we are going from a lighter medium to a denser medium. If it is bending away from the normal, we are going from a denser medium to a lighter medium. However, in lenses, we do not have a boundary which is perfectly flat, but it is curved. Because it is curved, therefore light when enters the denser medium will behave differently depending upon the type of the lenses. If it is a convex lens, the light will be converged at a point. If it is a concave lens, the light will be diverged, and in fact it would be expanding from the lens and will appear to be coming out from a point behind the lens. Now, let us see if we can use the lens formula to solve a problem. Or perhaps we can look at the other aspects of lenses. For example, in order to see very small objects, we use an instrument which is known as a microscope. A microscope is an instrument which enlarges or allows us to see very small objects. A simple microscope contains only one lens, and normally we call it as a magnifying glass. A magnifying glass, type of glass like this, is used to make things bigger, and we can say it can be used as a microscope. It is a simple microscope, and it is commonly known as a magnifying glass. Now, in the case of a magnifying glass, like it is shown on your slide, the object is placed between the focal point and the principal axis of the lens, point P. Now, a light which is coming from that objective O to the light, a ray which is parallel to the principal axis will, of course, pass through the focal point. I have indicated the focal point on both sides of the slide and of the lens, and therefore the line which is going to be passing from the focal point to the lens is not reflected, and that is one of the lines. The other line, we know any light which passes through the optical center is, of course, not refracted. When you join these two lines, they meet at a point I, which tells us where the image is, and as can be seen on the drawing, the image is going to be vertical. It is going to be magnified, but we say it is a virtual image because when I look at a magnifying glass, even though when I look through it, I see something magnified, but when I look at it from the side, I do not see an image. Therefore, the image which we see is virtual. It can be seen only when seen through the lens. Otherwise, it does not exist. Another question which is normally asked is, can we increase the intensity of light? For example, if we are receiving a light from a source, can we increase its intensity? Intensity, like if we remember correctly, was determined as amount of energy divided by amount of area. So if the amount of energy available at a circular opening is reduced, in other words, the opening is reduced, in other words, if we converge the amount of light, then the intensity, of course, has to increase. A converging lens is used, and a converging lens will increase the intensity of light. Yes, the answer to this question is we can increase the intensity of light. Now, another normal question which is asked is, let's see this lens. When I look at from the sides, it is very difficult to see whether it is thin at the edges or thick at the center, and we would not be able to, at one glance, see whether it is a convex lens or a concave lens. So how do we identify which lens is which if we cannot see the edges? The answer is very simple, that using the lens, we try to focus it to a point, and if the light is being converged, it is a converging lens, hence a convex lens. If the light is being diverged, it is being dispersed, it is, of course, a concave lens and a diverging lens. So much for this. Let us apply the relationship to the lens equation and see if we can solve a problem. On your slides, I have a question for you which says an object which is 3 centimeters high is placed at a distance of 15 centimeters from the convex lens, which has a focal of 10 centimeters. We have to find the position of the image, we have to find the nature of the image, and we have to find the size of the image. The data which we have is P, which is the distance from the lens to the objective, is 15 centimeters. Q, which is the distance from the image to the lens, we have to find out. The focal length is given, which is 10 centimeters, and we are given the height of the object, which is 3 centimeters. If we look at the lens equation, which is 1 over f is equal to 1 over p plus 1 over q, we find that the height of image is not depicted here, so we are not going to be using it for the first part of the question. Now, substituting the values, that 1 over 10 is equal to 1 over 15 plus 1 over q, we use everything positive, as we discussed last time, that in case of a lens, p is positive. If it's a convex lens, p is positive, q is positive, and f is positive. Substituting the values, we find 1 over q is equal to 1 over 10 minus 1 over 15, giving us q is equal to 150 divided by 5, or in other words, q is equal to 30 centimeters. So the image is going to be 30 centimeters on the other side of the lens. So if I have a lens, the object is on this side about 10 centimeters, the image would be about 30 centimeters to the other side. Now, what about the size of the image? The nature of the image, of course, we have identified. Because q is positive, therefore the nature is going to be a real image. Now, magnification is defined as the size of the image divided by the size of the object. So if the image size is larger, the object is magnified. If the image size is smaller, it is diminished. And it is also defined as the image distance divided by the object distance. This is something which we discussed last time. Now, substituting the value, we have the size of the image divided by the size of the object. The size of the object was 3, and this gives us 30 divided by 15, or rearranging, we find that the size of image is 30 multiplied by 3 divided by 15, giving us an object which is 6 centimeters. Because the image is now 6 centimeters, the object was 3 centimeters, therefore we have an image which is real, the image which is inverted, and the image which is magnified. Why is it inverted? Of course, if you look at the diagrams which we discussed last time, you will find that when we have a lens, object is on one side, and a real image is, of course, on the other side, becomes inverted. Let's look at another numerical. The object, same object, 3 centimeters high, now is placed 5 centimeters in front of the convex lens. So what we have done is we have brought it closer. Now it is 5 centimeters away from the lens, and the focal length is 10 centimeters. Again, the data is there. P is 5 centimeters. Q we have to find out. F is 10 centimeters. Putting it in the lens equation, 1 over f is equal to 1 over p plus 1 over q. We find 1 over 10 is equal to 1 over 5 plus 1 over q. Rearranging, we find 1 over q is equal to minus 5 over 50, giving us q is equal to minus 10 centimeters. Because q is equal to minus 10, that means that the image is going to be on the same side as the object. Now, the only one case in which we have image on the same side of the object, if it's on the same side, then the image is virtual, like in the case of a magnifying glass. Now, what about the size of the object? The size of the image, we in fact use the same relationship of magnification. Magnification is size of image divided by size of object, is image distance divided by object distance. In this case, we do not put the minus sign here because we are not concerned with the nature of the image or the direction of the image. We are just concerned with the magnitude. So we have size of image divided by 3 is equal to 15 divided by 5, giving us the size of the image is equal to 9 centimeters. So you have a magnified image, which is erect, virtual, and magnified. So this is the way in which we apply the lens equation. Now, in this lecture, what we are going to do is we are going to be looking at the application for humans. In other words, we are going to be looking at the human eye. We are not going to be looking at from the biological point of view. We are going to be looking at from purely physics point of view. In physics, when you look at the eye, it just behaves like a pinhole camera or an ordinary camera. You have a lens, you have a retina, which is in fact where the photograph is going to be made. So you have the construction as camera. You have an eyeball, which is your camera. It is filled up with a liquid, which the biologists know is the vertex humor, and the lens is made up of a soft material. But we are basically concerned only with 3 things. We are going to be looking at the eye lens, that is the lens, because we have been discussing lenses. We are going to be looking at the eyeball, because that is going to determine something which we are concerned with. And we are going to be looking at the retina. Retina is basically a membrane on which the image is made. Now, if you look at the eyes, the information is such that the rays which come on the eye pass through the pupil. We are not going to be discussing the pupils, which can increase or decrease depending upon the intensity of the light. And all the rays which are parallel to the x-axis or parallel to the eye pass through undeflected. However, the rays which are parallel have to converge through the lens, because it is a convex lens. They will converge and meet at the focus. Now, the eye is naturally constructed in such a way that the image is formed on the retina. Therefore, in the normal human being, if I'm looking at an object, I will always find that the object focus is in focus because the image is being formed on the retina. The lens is acting as the converging of light. A ray of light comes, it converges, forms on the retina, and the retina then through the optic nerve forms the image on our brain. Now, this is what we said was a normal eye. Eyes normally, people have defects in, and there are 2 types of defects which we are going to be considered with. One is we are going to be looking at the size of the eyeball. In certain cases, the eyeball naturally becomes larger or smaller. What happens with it? We are going to be looking at the lens. The lens, if it becomes thicker or if it becomes thinner, it will become thicker or thinner because the lens is controlled by ciliary muscles. The muscles, when they compress the lens becomes thicker, and when they stretch the lens becomes thinner. By this, what the eye does is it allows us to focus things which are nearer and which are further, thus bringing different things in focus, because when the lens becomes thicker, its focal length decreases, and when the lens becomes thinner, its focal length increases. Now, in both situations, what happens is that if either the eyeball or the lens change their shape, sometimes the image is not formed on the retina. Now, in case the image is not formed on the retina, we say that there is a defect in vision because the person is not seeing things clearly. Now, there can be different causes of the defects. The 2 main causes of defects are there might be a defect in the lens or there might be a defect in the eyeball. Now, when we look at, say, the lens, if the lens is thicker, the focal length becomes smaller. Now, sometimes it happens is that the ciliary muscles become very strong, or perhaps the lens becomes thicker due to some other natural circumstances. You might have some disease, or perhaps naturally by birth, this defect is there. So lens is thicker, this is the eyeball, the image is forming before the eyeball. Now, if it is forming before the eyeball, you will not be able to see. In the other cases, the ciliary muscles weaken with age. Just like in my case, the ciliary muscles are weakened, so I cannot focus something which is very near because the lens has now become thinner and the focus is behind the retina where the image is formed. Now, in these both cases, we have a situation in which we will not be able to see clearly, and therefore something has to be done to correct this problem. The other is the eyeball. Now, the lens is here, the eyeball, the retina is here. Now, in case the eyeball enlarges, which happens sometimes naturally, and it is naturally occurring, now if the eyeball is larger, then the image, of course, is going to be formed before the retina. In other cases, due to aging, the eyeball shrinks. Now, if the eyeball has shrunk, what is happening is now the image is being formed behind the retina, and again, you will not be able to see clear images. And in other words, your image is going to be distorted. These are the two defects of vision which we are going to be discussing. There are other defects, but we are not concerned with this because we are only going to be looking at the two types of lenses which we are going to be using. Now, the two types of defects which do take place, one is short-sightedness or myopia as it's called. The other is long-sighted or hypermetropia as it is called in biology or in normal everyday life. In both cases, what is happening is that you are not seeing objects clearly. Short-sightedness or myopia it is called is in cases in which you can see near objects, but you cannot see objects which are far away. What is the reason for this? It is the increase in thickness of the lens. If the lens thickness increases, the image is being formed before the eyeball or before the retina. In other words, or the diameter of the eyeball has increased. Again, you are having an image which is before the retina. In both cases, the image is being formed before the retina, and therefore you are not be able to see the image clearly. Like it is shown in your diagram, I have shown the thick line there indicates the place where the image is formed, or you can say that was the retina. In both the cases, in A as well as B, in normal thickness, you would have the image being formed on the retina. However, because the eyeball has increased or the lens has increased, the image is now being formed before the retina. In the first slide, which I'm showing you, the size of the eyeball remains the same, and you find out that with a thicker lens, you're going to get an image which is not on the retina. In the second case, in case the lens is the same and the eyeball increases, you get a similar situation in which the image is formed before the retina, and therefore you do not see clearly. How do we correct it? In order to correct it, what we have to do is, this beam which is to come, we have to enlarge it so that after refraction, it should fall on the retina. But we cannot really change the lens of the eyeball. That would require surgery, and normally it is not recommended, and because you can correct it even before that by using spectacles. So a concave lens is added. We know a concave lens diverges light. So when a light enters a concave lens, it expands or it is moving outwards, and then when it enters the eyeball, the image is then arranged. You have a lens of different powers, and you can therefore arrange it in such a way that light will now fall on the retina, and hence you can see a clear image. In case of long-sightedness or hypermetropia, as it is called, it is a type of defect in which distant objects can be seen, but near objects cannot be seen. I can look things which are very far away, but I cannot see things which are near. The reason for these defects is A, the decrease in the thickness of the lens. The lens thickness is decreased, so the image is being formed behind the retina. The second is the eyeball has shrunk. Again, it is formed behind the retina. This is a common example or a common occurrence in people who age. With age, this happens that as people age, your eyeballs shrink, and therefore you have long-sightedness. You cannot see things which are near to you. However, you can see things which are far away. Now, on your slide, I have given you the example. In case A, you have two images in which the lens is the same. However, because the lens eyeball is the same, the lens size has decreased. Therefore, the image is being formed behind the retina, and therefore you are getting a situation in which an image is not being formed clearly. On the second slide, I have the thickness of the lens is the same. However, the eyeball has shrunk. Again, you are getting a situation in which the image is behind the lens or behind the retina, not the lens, but the retina. It is behind the retina, and therefore, again, you are getting an image which is not formed clearly, and hence you are having a defect in your vision. This defect is very easy to correct. Again, that for nearsighted people, for far-sighted people, what we do is we use a convex lens. And before the eyeball, you place a convex lens. A convex lens converges light, and therefore what is happening is the combined focal length or combined effect of the two lenses is you are increasing the size of the lens, and therefore this image moves to the retina and a person can see more clearly. There is another type of defect which is astigmatism, but we are not going to be discussing that. You can always look at it up in your book or in references, and you can always see that in that you have a combination of lenses which are used to get rid of astigmatism. And astigmatism basically is a defect in which you can see things which are slightly out of focus as well as in focus. You can see some colors which are in focus and some colors which are out of focus. This is also a correctable disease. We are not looking at the causes of blindness because those come under biology and not under physics. In physics, we are basically dealing with the optical properties and therefore how to correct optical defects of vision. Now, whenever you go to an optician and you ask for a lens, you do not normally ask for the lens in terms of focal length. What opticians normally do is they have a terminology which is known as the power of a lens. Now, a power of a lens is defined as the reciprocal of focal length. In other words, the power is 1 over f, where f being the focal length, and the units of this power are diopter or meter inverse, or sometimes it's said it is per meter. Now, what is the significance of a power of a lens? Now, focal lengths, of course, can be 10 centimeters, 20 centimeters, 30, 40, 1 meter, or even 2 meters. And if it is, for example, 2 meters, 1 divided by 2 will give you 0.5. So a lens which has got a focal length of 2 meters would have a power of 0.5. Lens which has a focal length of 4 meters, in other words, the object is going to be focused, parallel light is going to be focused 4 meters to the right or to the left of the lens, then we say the power is 0.25. So that would give us an indication. Power is more easily handled by opticians, because when you go to an optician, you say, I require a power 1, power 1.2, or power 2. Technically, the optician will be able to translate that into the measurement and decide which lens is required. Now, what is the significance of the power? If the power is positive, then we say it's a convex lens. If the power is negative, then it is a concave lens. So a diverging lens will always have a power which is in the negative. A converging lens will have a power which is positive. So if I say my spectacles are 0.25, then that means the focal length of the lens out of which these spectacles are made is about 4 meters. And because I'm saying it is positive, therefore it is a converging lens. Lenses with higher power will have a smaller focal length, and lenses with a smaller power will have a larger focal length. So what we have discussed today is defects in the eye, defects in vision, and we have looked at the methods of correction and basically what we have said. Now let us pose a few questions to you. What happens to a ray of light which is traveling parallel to the principal axis? If a ray of light is traveling parallel to the principal axis and it falls on a lens, If the lens is converging, it is going to meet at the focal point. If the lens is diverging, it is going to diverge outwards, the beam is going to expand, but the expanded beam is going to appear as if it originated from a focal length behind the lens. So in both cases, when a parallel beam of light falls on a lens, it appears either to converge at the focal point, which is case of a converging lens, or it appears to have been emerging from a point which is the focal point of a diverging lens. And why do the thickness of lens change with passage of time? We are talking of the lens of the eye. The thickness of the lens will of course change because with aging, the ciliary muscles which control the thickness of the lens become weaker and they cannot exert the same amount of pressure. So the eye would like to focus at a certain point, but the ciliary muscles are weak, so eye will not be able to focus. It becomes thinner and the image is behind my retina, and therefore I need correction. Now, let us look at a numerical. For example, we have to find the power of a concave lens, which is a focal length of 5 centimeters. Now, because it is a concave lens, the data which we have is a concave lens. The focal length is 5 centimeters, which is 0.05 meters, and we have to find the power. So power basically is equal to 1 over minus f. The case of minus, because it is a concave lens, so power is 1 over 0.05, giving us a value of 20 diopters. So if I go to an optician and I say I want a lens of a power 20 diopters, the optician will immediately understand I require a very thick lens, which is a very small focal length. Now, in the 14-odd lectures which we have done with you, what we have done is we have looked at different aspects of physics. We started with the concept of the differences between science and humanities. We said in sciences are differentiated from humanities because science deals with the experimental method. Now, we discussed the experimental method, we discussed the essence of the experimental method, that the experimental method or the scientific method as it is called, basically has experiment as its root. Because in the scientific method, you observe something. When you observe something, you form a hypothesis. You give a statement that you are observing something, why you are observing it. Then once you have made this hypothesis or you've made this statement, what you do is you put this statement to a test. In our case, when we said, I have an object, I drop it, it falls. So I make a broad statement, objects when dropped fall. Now, then we put it to test. We take different types of objects. We take stones, we take rock, we take paper, we take a feather, we take a balloon, and we'll drop all of them and see what happens. We find the rock, the paper, the feather all fall, albeit at a different rates. However, the balloon rises, provided it's filled up with helium or hydrogen, it rises. So we have to modify our hypothesis, and this is basically the essence of our experimental method. And this is what differentiates a scientific method from a normal, and therefore sciences, only those subjects are termed sciences which follow the scientific method. Humanities basically do not follow the scientific method. Some might say, yes, they do follow the scientific method. However, when I say this hand, some of you might find this very attractive. Others might find this a very ugly hand. Someone else might find this just an ordinary hand. So now you have 3 sets of opinions about the same object. In sciences, one object will have only one set of values which will identify that object. For example, I say 1 liter of water is 10 centimeters by 10 centimeters by 10 centimeters container which contains water in it. The volume of that water is 1 liter. Whether I measure it in America, whether I go to Australia and measure it, whether I go to China and measure it, 1 liter of volume of water will occupy the same volume for all physicists, or in fact for all people everywhere. Therefore, in science, you have to be absolute, you have to be quantitative. And because we had to be quantitative, we said there was a need to have a measurement system. And in sciences, the measurement system which we follow is the International System of Measurement, or the SI system, and then we discussed its fundamental units. The fundamental units basically are the basis on which physics or other sciences are made. Then we looked at how we represent numbers, because in sciences we are dealing with very, very small quantities, like the size of an atom, which is 10 to the minus 27 kg, and then not the size but the mass of the atom is 10 to the minus 27 kg. Size would be around 10 to the minus 15 meters, something which normally we do not understand. And on the other side, if we are looking at very large quantities, for example, the mass of this earth, which is about 10 to the 24 kilogram, mass of the sun is around 10 to the 30 kilograms. I'm not giving you the number because I'm looking at approximations. So we have a range of masses from 10 to the minus 27 to 10 to the plus 30, and perhaps beyond if you're going to be looking at the mass of the universe, and so on, some things which astronomers normally do. In order to represent this, we said there are different ways of representing such large and such small quantities, bringing them in perspective. One was the use of prefixes and suffixes. The other was the use of the scientific notation. We then went into proper physics, and we just looked at, or we perhaps indicated, physics and its branches. We said classically physics has got a lot of branches. You have mechanics, you have waves and light, you have heat, electricity, magnetism, quantum mechanics, and atomic and nuclear physics. Whereas mechanics, waves and light, heat, electricity, and magnetism formulated classical physics, whereas quantum mechanics and atomic and molecular physics come under the compartment of modern physics. There are numerous other branches of physics which we are not dealing in this. For example, you might have semiconductors, you have lasers, and so on and so forth. However, these are the basic divisions we were looking at. Now, we were dealing with physics. And in physics, the first branch which we took up was mechanics. In order to identify mechanics, we said, okay, we are going to be looking at physical quantities. A physical quantity is a quantity which has a unit, which is represented in terms of fundamental units, and a number, and something which we can measure. Physical quantity is something which is measurable. We looked at quantities which has vectors and scalars. We said scalars have just magnitude but no direction. For example, mass is a scalar quantity. The number of students in this class is a scalar quantity because it is just a number. It does not have direction. Yes, some of you might say you have a direction. You're going from a lower class to a higher class, and that is the direction which you are following, but that is not the direction which we mean in physics. Vectors, on the other hand, have direction. For example, a point A to point B in this direction is a vector which would be about half a meter. However, I move around the table, I might have covered a distance of 4 meters, and that would be distance because it does not have direction. I'm going east, west, north, irrespective. But when I'm moving in a particular direction, I have a vector. Then we applied this understanding to different quantities like distance and displacement. We said distance is a scalar quantity, whereas displacement is a vector quantity. We applied this to speed and velocity and acceleration and retardation, whereas speed was a scalar quantity, velocity was a vector quantity, and acceleration and retardation both being vector quantities, where in acceleration speed is increasing or velocity is increasing, in retardation velocity is decreasing. We then did things with studied mathematical tools with you. We looked at graphs, we looked at how to formulate graphs, what to represent on the x-axis, what to represent on the y-axis. We looked at scales, proportionality, direct proportionality, and inverse proportionality. So if you have a quantity which is increasing in the x direction as it is increasing the y direction, we say it is a direct proportionality. If we have a quantity which is decreasing in one direction while increasing in the other direction, we say it is an inverse proportionality, and so on, so forth. Then we came to the proper parts of mechanics. We looked at force, we looked at inertia, we looked at the action and reaction. In other words, we looked at the Newton's 3 laws and we looked at their applications. For example, the first law basically stated, in other words, the law of inertia, that an object which was at rest would remain at rest. For example, I have an object which is lying here. If I come back tomorrow, again I look at this object, it is still lying here. Why? Because unless someone moves it or some force moves it, this is going to remain here. That is the essence of the first law. The second law basically told us that the more the force, the higher the acceleration, or in other words, force is proportional to acceleration. It also told us that force is proportional to mass. If it's a larger mass, I require a larger force in order to move it. If it's a smaller mass, I will require a smaller force to move it. So force and mass are also directly proportional, not inversely. In fact, mass and acceleration are inversely proportional. So larger mass with the same force, you would have a smaller acceleration. A smaller mass with the same force, you would have a larger acceleration. Then we looked at the equations of motion and how to apply it, how to derive the equations of motion, and where they are going to be used. We looked at matter. From mechanics, we went to matter. We looked at matter. We looked at weight and the states of matter. We looked at solid, liquid, gas, fluid, and plasma states. And we said, yes, there are states. And in other words, matter is something which occupies space. Mass is something which has matter in it, and so on and so forth. We then applied Newton's laws, and we looked at momentum, friction. These were the uses of laws. And from these, we came to the concept of work. Now, in the beginning, we said physics is a science which A, does measurements. In other words, we looked at fundamental quantities. And B, it looked at interplay of energies. In other words, we were looking at how to change or how to convert one form of energy into another form of energy. Now, in order to be able to convert one form into another form, we had to look at the concept of work. Because the ultimate idea of having some energy is to put it to some use. And to put it to some use, basically we have to get some output of it, or in other words, we had to utilize it to get work. Now, in physics, we say work is only done when a force is applied and the object moves in the direction of the application of the force. Now, if I'm walking around this room, I'm not doing any work against gravity, which is, of course, vertically downwards. If I'm moving in the horizontal direction, the vertical direction is in which the gravity is, then, of course, I have not done any work. We then looked at the types of energies. We said there are lots of energies. We have solar energy, tidal energy, we have wind energy, we have chemical energy, and so on and so forth. But for our purposes, because we were confined to mechanics, we looked at only the types of energy. We looked at elastic potential energy, gravitational potential energy. We looked at the kinetic energy, and we looked at the law of conservation of energy. The law of conservation of energy, which allows us to solve different problems or look at different conversions from one type of energy into another type of energy, basically states energy can be converted from one type to another type. However, it cannot be lost or it cannot be created. And from the types of energy, we went on to the concept of efficiency. Now, the law of conservation of energy tells us that energy can be converted from one type to another type. We are basically interested in the usage of energy to produce work for us. Now, the type of energy which we are interested in is known as useful output. However, whenever you do work, some of the energy is used into useful output. This is type of energy or type of work we would like that system to do. But some energy is lost to the surroundings, or in other words, that energy is wasted. So we have some output and we have energy which is being input. So useful output divided by the input, which is the amount of energy we are adding to the system, basically is the efficiency. And the example of this was the motor vehicle. So the amount of energy which is coming in burning of fuel, about 35% goes into driving the vehicle or providing the kinetic energy, whereas 55% or 65%, depending upon which type of vehicle you are looking at, if you have efficiency of 35%, then you have got a wastage of around 65%. So 65% of the energy is lost as heat to the surrounding. Because it is, this energy is not being used in the output which we desire, that is the movement of the vehicle. Therefore, we say that is non-useful energy. So efficiency of the car would be 35%, or in other words, 35 units of the 100 units which you have added to the motor vehicle are giving us useful output. Now, from mechanics, we moved on to the next topic which we took up with you. That was heat and thermometry. And when we looked at heat, we said, what is the difference between heat and temperature? We said heat is the amount of energy which an object possesses, whereas the temperature told us the degree of hotness of that material. From this, we said that whenever you provide energy to something, it expands. We looked at expansion, and of course, once we are looking at expansions, we are going to be looking at the usefulness of that for our purposes. In other words, if a liquid expands, it allows us a technique or a way to measure temperature, because if at 0 degrees, this is the size, at 100 degrees, this is the size has gone from A to B. So this is the amount of increase that has taken place. If we divide this by the number of degrees which we have, if you are looking at the Celsius scale, at the freezing point of ice, which is 0 degrees Celsius, at the boiling point of water, which is 100 degrees Celsius, the difference is 100. So we can now measure a scale. In other words, the expansion of liquids and gases allowed us to form a temperature scale. We looked at the 3 temperature scales with you. We looked at the Fahrenheit scale, we looked at the Celsius scale and the Kelvin scale, and we looked at the intercomparison, how to convert temperature which is in one scale into another scale. We looked at thermometry and so on and so forth. We then came to the gas laws. We looked at the Boyle's law and the Charles law, that as you increase the pressure of a constant volume, of a constant mass of gas, the volume has to decrease. And when we looked at the Charles law, that as you increase the volume, the temperature has to, if the temperature is increased of a constant mass of gas, then the volume also has to increase, and combining them into Avogadro law and so on. We found the general gas equations. We looked at the specific heat capacities. We found the techniques to find the specific heat capacities and how to find how much heat energy a certain object possesses or does not possess. So we said that, okay, the specific heat capacity is defined as the amount of energy required to change the temperature of 1 unit, which is 1 kilogram of a material, by 1 degree Celsius or 1 Kelvin, which is the specific heat capacity. And in the case of heat capacity, of course, it is the heat possessed by any object because of its particular temperature. From this, we moved on to optics. Now, because optics, light is also a type of energy, but we were not looking light from terms of energy, but light behavior as from optics, to how to use light in optics. So we looked at the principles which govern the propagation of light. A, that light moves in straight lines. B, we looked at the principle of reversibility. We discussed it, that if light moves from point A to point B, then the path it has taken from going from A to B, if it moves from B to A, it should follow the same path, which is the principle of reversibility, which in other words says, if I can see you, you should be able to see me. And we applied these to the different laws. We said that when in one material, an object, a light strikes an object and it is reflected, then it has to follow certain laws, which are known as the laws of reflection. The laws of reflection being 2, it said the incident angle and the reflected angle have to be equal. The incident ray, the reflected ray, and the normal have to lie in the same plane. So in other words, light coming along the surface has to bounce back along the same surface rather than bounce upwards or downwards, which allows us to geometrically find out where light would be reflected and how to reflect it from plane surfaces, we looked at the formation of image in mirrors, and we said when we look into a mirror, the object is in front of the mirror, the distance behind the mirror as well as the object to the front of the mirror has to be equal, and we discussed this case with you. Then we looked at the formation of or the behavior of light when it struck a surface which was not plane. In other words, when light strikes a curved surface, what happens? So we looked at the two general examples, which was a concave mirror and a convex mirror. When you have a concave mirror, the light bounced from the mirror and was converged at a focal point. And we looked at the equation, we formulated the mirror equation for concave mirrors, and we looked at convex mirrors, and when light came, it bounced off. In other words, we looked at the process in which mirrors can be used to focus light or to defocus light as it is, and we found out that concave mirrors are basically used when you are going to want a source of light giving a parallel beam like in car headlights, and it was used in telescopes, but we did not consider the telescopes. We then derived the mirror equation with you, which was 1 over P plus 1 over Q should be equal to 1 over F, which was similar to the 1 or identical to the 1 which we have derived in the last lecture for the lenses. Then we looked at the concept of magnification. We said when you are magnifying some things, it is the size of the image divided by the size of the object, which is magnification. And then after looking at magnification, we moved on to the last topic, which was done in the last lecture, which was refraction of light. Now, refraction of light, when we looked at refraction of light, we said light moving from a lighter medium to a denser medium, when it strikes at an angle, is bent. And we looked at the reasons for its bending. The reasons for its bending is basically when light is traveling in a lighter medium, it is traveling at a very high speed. When it is traveling in a denser medium, it slows down. Because of this effect, the bending takes place, because the distances covered in the same time, of course, is different. So it is covering a larger distance here, it is covering a smaller distance here, just because it is moving at a smaller speed. Therefore, it has to naturally bend. We then looked at the critical angle. Refraction of light allows us to formulate the relationship for critical angles. A critical angle, basically, like we just said at the beginning of this lecture, you have to move from a denser medium to a lighter medium so that light can bounce back. If the angle at which it strikes gives us an angle of incidence in the lighter medium greater than 90, then of course light cannot escape from the denser medium to the lighter medium if it is greater than the critical angle. And we looked at the concept of total internal reflection, and we looked at how total internal reflection is then used in prisms and in optical fibers. And we looked at different devices which were made using prisms. In prisms basically were used in binoculars, and prisms were used in periscopes. And the optical fibers, of course, you had a series of optical devices which could be used in the medical profession, and those devices, endoscopes, which allow doctors to look inside a patient. You have a very thin wire, about 1 centimeter thick, which contains an optical fiber plus other small pipes through which you can either have a suction, you can introduce fluids into the body, you can extract fluids out of the body, you can also have small instruments to cut or do something. And in angiography, basically, a small ring is placed using an endoscope, and you just enlarge a vein which has become constrained due to some biological defects. And of course, we then looked at lenses, we looked at the lens equation and application of lenses. And what we have done today is basically looked at the human eye. We have looked at the different defects of vision, or what we have looked at the two defects, which A can be either due to the enlargement of the eyeball, B due to the thinning of the lens. In this case, you have the image which is forming in front of the retina. In order to correct this, you had to place a diverging lens So the diverging lens just moved the image back on the retina, and the vision was corrected. So we looked at the two types of defects of the vision. We looked at nearsighted, which is corrected by using a concave lens. You looked at the defect, which is known as farsighted, or hypermetropia, which is corrected with using a convex lens. So we have now gone over 14 weeks with you, or 14 lessons with you, and we have tried to give you an understanding what exactly is which we physicists do. We have just touched a very small portion of everything which physicists do, and we have tried to just instill into you a spark, an idea that physics is something which gives you an understanding of what is happening in everyday life. And people who want to go more into detail, want to find out more about the things which we have discussed, or in fact want to find out even more about things which we have not discussed, can look up at texts in physics and find out exactly how things work and what is it that the contributions of physics and the physics community have done in this. Thank you very much.